So today we are going to continue our discussion on dynamics of rotational motion. Today we are going to learn about the centripetal acceleration and derive the expression for the centripetal acceleration. So what is centripetal acceleration? Now consider a particle moving in a circular path, right, with uniform speed. Now this particle will possess an acceleration which is always directed towards the normal to the path of the particle, which means that the acceleration will be directed towards the center of the circle in which it moves. For example, if I draw circle and a particle starts moving from here, right? So when the particle has this point P, the acceleration will be towards this. If it is here, suppose at point Q, the acceleration will be directed towards this point center. If it is at R, the acceleration will be towards this point. If it is at S, the acceleration will be towards this point, right? And the body is moving, or the particle is moving with this velocity. The velocity is tangent, right? Velocity is tangent to that point. So now let us see the derivation of the expression for the centripetal acceleration. Let us consider a particle rotating with uniform speed v. See, this is the particle which is at point P, and it starts rotating with a uniform speed omega, and it has a uniform linear speed v, right, in a path of circular radius r, right? It is rotating in a circular path of radius r. Now at the instant initial, the particle is at P position. Now after a small interval of time t, after a small interval of time t, the particle moves from P to Q. The particle moves from P to Q. So at t equals to 0, it was at P, and if t equals to t, it is at point Q. Okay. So the angular displacement of the particle is POQ theta. The angular displacement of the particle is angle POQ, which is equal to theta. Let us assume. Now, the linear velocity of the particle we know is always directed along the tangent to the circle. This is the linear velocity here. This is the linear velocity at Q. Means the linear velocity at point P is directed towards PR, and the linear velocity at point Q is directed towards QS. Okay. Now the tangent to the circle is normal to its radius. This tangent QS and PR are perpendicular or normal to the radius. This is the radius OQ, which means QS is normal to OQ, which means QS and OQ, the angle is 90 degree. Between QS and OQ, the angle is 90 degree, and between PR and PO, the angle is 90 degree. Okay. This you have learned in mathematics. Okay. So the linear velocity v of the particle, this v of the particle has no component along this direction. This QS, this velocity has no component along this direction, and this velocity v, which is directed towards PR, has no component along PO. This has been discussed in the chapter vectors. Okay. Now, what we are going to do, we will resolve the velocity at Q into two rectangular components, QA and QB. QA and QB. One is vertical, QA is parallel to PR, and QB parallel to PO. We will resolve QS into two rectangular components such that one component QA is parallel to PR and another component QB is parallel to PO. Now, as we know that angle POQ is theta, so if PO is parallel to QB and QO is the transversal, so we can say that angle OQB is also theta. Angle OQB is also theta. This angle is also theta. Now we know angle OQS is 90 degree. So angle BQS is 90 minus theta. BQS is 90 minus theta. Again, we know that angle AQB is 90 degree. This angle is 90 degree. So angle SQA or AQS is 90 minus of 90 minus theta, which gives you theta. So we see that angle AQS is equal to theta. So we can write that QA is equal to V cos theta and QB is equal to V sin theta. Okay. So we have resolved the velocity at point Q into two components QA and QB, and their values are V cos theta and V sin theta respectively. Now we will assume that the distance between P and Q is very small, which means Q is a point which is very near to P. So if P and Q are very near to each other, then theta, the angle theta is very small. If angle theta is very small, cos theta is equal to 1. So QA is equal to V. And sine theta for very small theta angle is equal to theta. So we can write QB is equal to V theta. QB is equal to V theta. Now we see that QA, the velocity is V. Now QA was parallel to PR. QA was parallel to PR. So the velocity is V here also, and we have got QA is equal to V. So there is no change in velocity. So there is no change in velocity along the vertical direction, right? There is no change in velocity, but along the horizontal direction, that is towards the center, the velocity was initially zero, as this PR didn't have any component along PO. So the initial velocity was zero, and now the final velocity, or at the velocity at time t equals to 0, it is equal to V theta. It is equal to V theta. So there is a change in velocity. So the change in velocity is 0 to V theta. So V theta minus 0 is the change in velocity. And if we divide this change in velocity by time, sorry, my mistake, V theta minus 0 by time, we get the acceleration. We get the acceleration. Acceleration is A. We get the acceleration A. So A is equal to V theta by t. So if A is equal to V theta by t, we know what is theta. We can write theta is equal to omega into t. Theta is equal to omega into t. Omega is the angular acceleration. So we get V dot omega. So the centripetal acceleration is equal to V dot omega. The centripetal acceleration comes out as V dot omega. Now we know omega is equal to V by R. So we can write it as V square by R. We can write it as V square by R. Also, in terms of omega, V is equal to omega R. V is equal to omega R. So we can write this as omega square R also. So the centripetal acceleration is either V into omega, linear velocity into angular velocity, or V square by R, or omega square into R. These are the three expressions for the centripetal acceleration.